Continuing our discussion on the absorptiometric methods, we have discussed so far about the metallic about the atomic structure and how the absorption bands occur because of the molecular bonding, and then we have also discussed the electromagnetic radiation and followed by spectrophotometry. What are the basic theory of spectrophotometry, followed by instrumentation for absorption, methods to work out the absorptiometric methods, and then we have also discussed about the Beer-Lambert's law, relative concentration error, followed by nephelometry and turbidimetry. And then we have had a discussion regarding fluorescence, phosphorescence, and now I want to talk to you about another related technique, that is chemiluminescence. In chemiluminescence, the principle is same, that is the radiation coming out of a chemical reaction in a colored form can be monitored. Here the difference is the initial incident radiation is not very important. The chemical reaction itself will generate a compound which will give out particular color. So, this method is known as chemiluminescence. This technique is known since quite a long time, and but the application of chemiluminescence in analytical science is a very recent development. Normally spectrophotometry, turbidimetry, fluorescence, nephelometry and phosphorimetry and all these things are normally carried out in solutions. But the main difference is chemiluminescence can happen in gaseous medium also, as well as in liquid medium, aqueous medium also. So, but the essential principle is monitoring of color produced in a chemical reaction. So, there is certain amount of overlapping of the techniques, but the instrumentation has to be entirely different and much more simpler, because we do not need so many monochromators and things like that for chemiluminescence measurements. So, the application, several compounds in the environment react with chemical species to give chemiluminescence. So, can we use this technique for the for the determination of the pollutants? Now, you will appreciate that there are different kinds of pollutants in the environment. One is air environment, one is liquid environment, another is solid environment. And if we have a liquid environment, the basic idea is to bring the analyte into a colored solution, colored format, by reacting with a chromophore and then determining the substances. But suppose I need to determine a substance like sulfur dioxide or nitrogen oxide, that is in the air. So, the attractive feature of chemiluminescence is that the reaction can be carried out in the, if I can draw a small amount of air sample into a reactor and then make it undergo the reaction, and this reaction can be monitored using the same monochromators, detectors and other things also. So, I can do it for the environment in the air as well as environment in a liquid form. The beauty of this system is the simplicity. I just have to bring the reagents together, let the reaction proceed, and the moment reaction proceeds, there will be certain amount of color developing, and you can see virtually in your reactor, if you allow particular reactions to take place according to chemiluminescence measurements, then you can actually see the color, but monitor it instrumentally to determine them at very low levels, etc. That is the beauty of spectrophotometry or any spectroscopic method, that permits you to determine the substances in microgram, nanogram levels. So, the extreme sensitivity that you obtain normally in chemiluminescence is because of the specific chemical reaction with only known compounds, and other compounds do not react at all. They remain mute spectators to the event of chemiluminescence. And same thing is true with respect to selectivity also. In selectivity, what we normally look for is the reaction should be specific to a particular compound. No, it does not react with other compounds to give similar colors. Otherwise, it will create in difficulty for isolating the desired radiation. So, because of these advantages, they have propelled the development of chemiluminescence techniques. Nowadays, we have chemiluminescence techniques for sulfur dioxide, NOx, etc., which are air pollutants, not in the liquid form. So far, we have been talking only about the liquid form, but now we may even talk about these things. So, basically what is a chemiluminescence reaction? You can see here A reacts with another compound B, that gives you a chemical C, that is the excited species C, and it also gives out certain amount of radiation, okay, mu D, and this C star is the excited species which reverts to ground state, allowing the radiation to come out. So, the radiation intensity, the ICL we write it, that is photons emitted per second. It depends upon the rate of production of dC by dt. See, dC by dt is the rate of production, and the quantum yield also is important, because that is the number of photons per molecule reacted, which in turn again depends upon the quantum yield phi x, that is excited species of the per molecule reacted, excited states per molecule reacted, that is the fluorescence intensity, and the emission quantum yield, that is photons in the excited state. To put it mathematically, what I normally write is ICL is equal to phi CL dC by dt. This phi CL is a product of two functions, that is phi x excited and emitted. So, analytically useful chemiluminescence have values ranging from, for this phi CL, ranging from 0.01 to 0.02, that is the proportionality constant. So, if I have that, I can determine the I can relate the intensity to the concentration, that is the whole logic. So, instrumentation consists only of a suitable reactor. All you have to do is design a suitable reactor and select the radiation, put a photomultiplier tube in front of it and determine the current and correlate it to concentration. So, it is sometimes dependent, which time dependent also, because all the reactions do not take place in the given reactor at the same time. So, it reacts, each molecule has to react. So, if you are carrying out an air reaction in an air sample containing a chemiluminescent compound, then it takes time for the reaction to start and proceed and reach a completion, and then fall back on the equilibrium level. Okay. So, the chemiluminescence signal, we have to understand that it is a time dependent reaction. So, it slowly rises to a maximum and then it falls as the reactants combine, and once the reactants are consumed, there will be a decay. That decay would be exponential after the event. So, for quantitative analysis, the signal is integrated for a fixed time. We have to fix the time and collect all the photons that are generated in the photomultiplier tubes, and then integrate it, have a certain number instead of the current or something like that. So, it is known as photon count. You can plot photon count versus concentration also, and the signal is integrated for a fixed time. Time is important for us now, and we have to compare with a standard. Again, we see most 99% of the spectroscopic methods, they are all relative. So, all your results would be as accurate as your standard. So, there is lot of chemistry and then precaution and then quality maintenance involved in the standard preparation, standard handling, standard storage. So, all these things compared with if I have a full control over the standard, my result will be more reliable. So, either we can, since the event itself is a very dynamic event, that means initially there is no reaction, slowly there will be a reaction, it will reach a maximum, and as the signal dies down, it will come back to ground floor, it will come back to the base level. So, it is a dynamic signal, and once if it is a dynamic signal, I can always go for the peak height or peak area. Normally, in 99% of the spectroscopic measurements, peak height is used, especially if the signal is very strong and very specific. But if the signal is weak and broader, very broad, then peak area is more important, because the matrix components will affect the shape of the peak quite often. So, it is important for us to remember, if the peak is sharp, go for peak height. If the peak is broader, you should always go for peak area. So, for quantification, either one we can use, and both will be equally good. I personally prefer peak area integration because it can be done by the computer, that is number one, and then it reflects the changes in the matrix with respect to the reagent as well as time. So, the difference between the starting event and ending event, whatever is the excitation, all the events will be covered in peak area, but not in the peak height. So, that is a very important consideration, especially in spectroscopic this thing. Quite often in ICP and atomic absorption, the peaks are so sharp that the area measurement does not make any difference at all. So, in that case one can go for peak height determination. So, for example, look at this signal, the chemiluminescence signal as a function of time. Initially it will be 0, and then slowly emission intensity will increase. Once it reaches with respect to particular time, then this excimer will come back to the ground state, and then chemiluminescence will die down. So, in this case you can see that the peak is quite broad, and you can peak height also you can use, and peak area also you can use, because the peak area does not have too much complications. It seems to be a fairly decent peak without much variation in the signal with respect to blank as well as sample. So, in this case we can go for either for peak height or peak area. Now, I am not going into the instrumentation of the system, because obviously such instruments are 99% of the time they are all dedicated instruments. For example, if you want to determine nitric oxide in air, all you need is a box containing the reactor and the associated optics and detector. So, we have covered most of the things except the reactor, and reactor is a matter of design. Okay. So, each manufacturer will have a different kind of design. What is important in chemiluminescence reaction is to bring the analyte and the reagent together in a given space of either a flask or a reactor or a multiple slots in a given container, where reagents can be added, reagents can be subtracted, or you can add buffer. You need a sample to draw the sample from air. You need a pump and other associated equipment, but all other things are a matter of detail rather than convenience. So, each manufacturer expects to produce a chemiluminescence system which is very specific to his needs. Again, I have to emphasize here that there are no standards available for measurement of chemiluminescence. So, what do? We take pure reagent or pure analyte itself and note down the chemiluminescence value. It can be either peak height or peak area, but the delivery of the reagent and allowing time and the reactor size, all these become important to note down the signal. So, the sensitivity of the system depends more on the design factors rather than the instrumental factors. So, 99% of the time you come across equipments, chemiluminescence equipments, which are dedicated instruments. For example, if you want to determine sodium, nitric oxide in the air, it is a very common constituent coming from vehicles, etc., and also from atmospheric reactions. Whenever there is lightning, there will be nitric oxide will be produced. So, in such cases, it is important for us to determine nitric oxide in the environment. So, the manufacturer will produce a dedicated instrument for the measurement of nitric oxide, and for which the reactor design and everything is his. So, the analysis of nitric oxide is one typical example. So, you can see in the slide what I am showing you is this nitric oxide will react with ozone. That means, in the reactor you have to supply ozone and draw nitric oxide from the environment through a pump or something like that, allow it to react with ozone, which will give you an excited species NO2, that is nitrogen dioxide, and that nitrogen dioxide excited species will decay into nitric oxide plus H mu, and the radiation is somewhere anywhere in this region. You can go for measurement using a filter or a monochromator or slate or anything like that, depending, but anywhere in this range you can go for that, because if you remember, the peak seems to be quite broad in chemiluminescence. For example, you can see here the peak is quite broad, and the wavelength need not be fixed at all, but you can fix it also and make the measurements. So, what is so special about this? The speciality is linear response is from 1 ppb, parts per billion, to 10,000 ppm. So, the order is approximately 5. Nitric oxide can be determined 1 to 5 order, that is 0.1 molar, 0.01 molar, 0.001 molar, 0.0001, like that you can go down to 0.40 1 molar. And this is important. So, this reaction is used for nitric oxide determination from ground level to altitudes as high as 20 kilometers. So, again this places some sort of a restriction that your equipment should be portable and it should fly somewhere around up to 20 kilometer, or you need to draw a signal from as high as 20 kilometer to the ground where the instrument is kept. That means a sample needs to be drawn at that level. So, that is the beauty of chemiluminescence, especially nitric oxide. So, suppose I want to do the nitrogen dioxide. So, nitrogen dioxide it reacts around 700 degrees to decompose to nitrogen and oxygen. It is a very common well known reaction. So, but this nitrogen and oxygen can recombine to give you nitric oxide, and nitric oxide can react with ozone just like in the previous signal. This nitric oxide and ozone ray same reaction scheme will continue. It will produce NO2 excimer, NO2 excimer will degenerate to NO2, and then the NO2 can be we do have some sort of wavelength to monitor. Now, the nitrogen dioxide is important from the point of view of environmental pollution, because nitrogen dioxide comes out from the vehicles on the road. So, obviously, here the instrument is not drawing a sample from anywhere except from the automobile exhaust. So, I need to have a sampling system from the exhaust into the chemical reactor, that is the box and then instrument. So, here the here the determination becomes very simple, because all I have to do is take the vehicle to the equipment and then finish the determination. Now, phosphorus is another element which burns in air, hydrogen, and that will give you HPO star ion, and the lambda max is 526 nanometer. That means, it gives out a radiation corresponding to 256 nanometer. So, I can always go for the determination of phosphorus using that reaction. Now, if I can react with ozone and nitric oxide, can ozone itself be determined in a given environment? Because this is a question gains importance, especially because ozone is an atmospheric contaminant, and it is also required to stop the radiation coming from the solar system, and all of us know that chlorofluorocarbons and many other compounds, they do lose, they destroy the ozone layer in the environment. So, we can determine ozone, but on the ground ozone is again a very corroding chemical, and it is considered as pollutant, especially in cities and towns and near the beaches. So, ozone can be determined by its reaction with rhodamine B adsorbed on silica gel. What I do is I take silica gel, put rhodamine B in that, and then I allow it to react with ozone, and the ozone range can be from 1 parts per billion to 400 parts per billion. Normally, the ozone content is only in the range of about 1 to 0.1 to 1 ppm or something like that, but it can be determined at higher levels. It can also be determined by reacting with ethylene. Both these reactions are almost specific for ozone. Nothing else can interfere in the determination. Okay. So, there is a determination of sulfur dioxide. There is a specific dedicated equipment available for the determination of sulfur dioxide also. Now, I have not informed you the cost of such equipments, especially the chemiluminescence equipments are very popular for the determination of ozone, and then nitric oxide and nitrogen dioxide, sulfur dioxide, etc. The cost of these equipment varies from 15 to 25 lakhs. So, they are compared to spectrophotometer, chemiluminescence equipments are quite costly, but depending upon the importance of these species in the environment makes it worthwhile to have it. Again, I have to inform you that in India we do not produce chemiluminescence equipments. India is an underdeveloped country as far as equipment monitoring equipments and spectroscopic instruments are concerned. 99% of the time we end up importing the importing the instruments, but we are good at using the equipments. Now, that brings me to another application, that is determination of sulfur dioxide. That is the reaction I am presenting to you here, that is 4 hydrogen molecules can react with 2 SO3 molecules to give you a sulfur molecule and water, and sulfur molecule can excited sulfur molecule can get deactivated to sulfur and giving you a radiation of about 384 and 394. You can monitor the reaction at either wavelength, and then sulfur dioxide can be determined again by chemiluminescence method. And then this is a very beautiful reaction, that is luminol reaction. This luminol is a compound given here. It is an amino compound basically, and the fused ring with 2 amino groups and then 2 CO groups, and it can react in an alkaline medium. I have written 2 OH minus here, and this alkaline medium, in this alkaline medium atmospheric oxygen can be determined, and the reaction is represented as, this is NH2 remains as it is, this group, the NH-NH bond breaks, and then we get COOH and COOH, that is diacids, amino benzoic acid. Then the other reaction products are very simple products like nitrogen and hydrogen, but the reaction is accompanied by the emission of H mu. The radiation corresponds to 425 nanometer. This product is known as luminol. Okay. CO2, chromium and copper, all these ions catalyze this reaction. Especially whenever I am talking about catalysis of a reaction, we are talking of about microgram or nanogram level of the materials. So, determination limits are of the order of 0.01 nanomoles per liter for carbon dioxide for cobalt, and 0.5 nanomoles per liter for chromium 3, and 1 nanomoles per liter for Cu2 plus. You can imagine what would be the laboratory conditions to work at this level. The extreme precautions which I have been again and again emphasizing to teach you all these things are very important, and we should be very careful whenever we are talking about determination, especially quantitative determination using spectrophotometry or spectroscopy, either way. So, this brings me to another final presentation, maybe this is my final presentation today, that is the determination of organic species. Several organic species like this uric acid, it is a part of our urine, and uric acid can be reacted with oxygen to give uricase, that is in presence of urease enzyme, and that gives a compound known as allantoin, and H2O2 is produced. Glucose, cholesterol, choline, amino acids, aldehydes and lactates have been detected in this way, because in many of these cases the reactant can change, and in presence of these reagents, sucrose and water, alpha D glucose, and alpha D glucose can mutarotate to beta D glucose. Beta D glucose can react with oxygen in presence of this glucose oxidase to give you gluconic acid, and H2O2. Now you have the gluconic acid, you can just add H2O2 and luminol, that is the sequence leading to chemiluminescence. The detection limits what we get is of about 1.1 picograms. Detection actually it should be picogram, 0.1 picogram to 100 picograms we can determine. So, this brings us to the end of discussion about the spectrophotometric equipment, related techniques and the practice. Now, in the next 4 classes I want to take you through a procedure where we can use a method using the spectrophotometry or fluorescence or any other related technique for the determination of these things. That itself constitutes a separate science by itself, because you will have to understand the chemical reactions and then possibly the other related terms with respect to analytical science will come into play. So, I suggest you read your chemistry properly, and especially the chemical reactions which I am going to present to you for about 20 parameters for pollution monitoring. That is where we are going to concentrate in the next 4 classes. So, thank you very much.